Hi. I just wanted to, now that I got this working, I wanted to show everyone something that came up in an office hour, talking about how a saturated salt can represent equilibrium. This is a simulation through PhET, through the University of Colorado. I can include a link to it in the description. But when you turn on the simulation, you can totally look at how a table salt works. And when you shake a table salt, obviously you can see that the ions dissolve into water. I would imagine that if you kept adding salt, eventually we would reach saturated. But the important thing to talk about here is we're now looking at these particles on the particle level. You can see that the volumes of solution are very, very low here. We're approaching, what is that, nano, picoliter, femtoliter, very tiny fractions of a liter here. So to look at, I want to look at a slightly soluble salt so that we can see what it looks like when it reaches the saturation point. I'm picking Mercury 2 bromide. You may know from table F that the halides are insoluble when using the Mercury 1 ion, dimercury. It's also true that the Mercury 2 ion, though it's less common, is also very low soluble. A couple more shakes. Pay some attention to the numbers of bound and dissolved over here. You can see that a crystal settles on the bottom, and this would be saturated. We have undissolved solute on the bottom of our container. As we look at these numbers, we can see that they're holding steady around 15 and 30 for the dissolved, 16 and 30, 16 and 32. But I want you to look at this bottom crystal. Being saturated doesn't necessarily mean that the dissolving stops. The particles are still dissolving off. What's new, and you can actually see it at various points on the bottom of the container, and dissolve. This means that it's not that dissolving stops, it's that crystallization starts, and then this would still fit our definition of equilibrium, where the opposing rates are the dissolution and the crystallization, where the rates are equal. For each ion that comes out of solution, another ion comes into solution. And if you've been watching this over the course of this video, you can see that that's actually happening. That one's falling off, one's coming on, one's falling off, one's coming on. And that the amounts, the concentrations, are constant. So looking at the number of dissolved particles here, we're still holding it 15 and 31, 15 and 32, 14 and 32. It's bouncing around, but it's remaining relatively constant. If we were to graph it over time, it might be a bumpy line, but it would be overall flat. As you can also see that the bound amount is also holding steady, even though the individual particles are switching place. I hope this clarifies things a little bit to see one particle representation of equilibrium and how it takes place inside a container. Thanks for watching.